Hello, welcome to Regular Achievers Educational Limited. Today we are going to be moving forward by looking at Paper 2 AQA GCSE Physics Review. So far we've been able to look at Paper 1 topics, and we are going to proceed today by reviewing the Paper 2 topics. And here are the list of the topics for Paper 2, ranging from forces to waves, magnetism and electromagnetism. Then we have space physics. So we start with forces today, and thereafter we are also going to review a past paper that has to do with the topic forces. Forces. In this topic, we will explore how forces affect motion, balance, deformation, and pressure, from everyday pushes and pulls to advanced ideas like momentum and safety in collision. Scalars and vectors. Scalars have only size, which is also referred to as magnitude. An example of such, we have speed, distance, time, and mass. Vectors have both the size and direction. An example of such, we have the velocity, acceleration, force, and momentum. Vectors can be shown as arrows because it's going to show you the direction that is moving, okay? Where they act, and their length also shows their strength. How long it is shows the strength in which they move in that direction. An object moving in a circle at constant speed is still accelerating because its direction changes continuously. Contact and non-contact forces. Contact forces occur when two objects touch. For example, friction, tension, normal contact forces like your pull and push. But non-contact force acts at a distance. There is no need for touch to take place. For example, the gravity, the magnetism, and electrostatic attraction. Every force is an interaction between two objects. If one pushes, the other pushes back with an equal force. Weight and gravity. Weight is the force that is caused by gravity acting on a mass. So the formula we use is weight equals to mass times the gravity. And the gravity on Earth is given as a constant value of 9.8 Newton per kilogram. So weight acts through an object center of mass. Your mass stays the same everywhere, but your weight changes depending on the planet's gravitational field strength. Resultant forces. When several forces act on an object, they can be replaced by a single resultant force. So if forces are balanced, object stays still or moves at constant velocity. But when it is unbalanced, the object accelerates in the direction of the resultant force. Example, a skydiver speeds up at first. So the weight is greater than the air resistance, then reaches terminal velocity when both forces they are balanced. Work and energy transfer. We know that work done equals to force times distance along the line of action. So we can say work done equals to force times distance, and the unit is joules. So work transfer energy, for example, when you lift a book, it gives it gravitational potential energy, and work done against friction always increases the temperature. Stretching springs and Hooke's law. To stretch or compress an object, more than one force is needed. And Hooke's law makes us to understand that the force is directly proportional to extension until the limit of proportionality. So that's why we have force equals to what? The constant times this extension, which is represented with X or E. So the spring constant K shows the stiffness, the elastic deformation returns to its original shape, and the plastic deformation permanent change is going to happen in the shape if it's an plastic deformation. Work done in spring. Energy is stored as elastic potential energy in stretched or compressed springs, and the formula is the energy is half k e square, or you say half ks square, it's still the same thing. So the work done to stretch a spring is equals to the energy stored if within the elastic limit. Moment. Moment equals to force times the perpendicular distance from the pivot. So we have the moment equals to force times distance. So a force causes a turning effect about a pivot. So if total clockwise moment equals to the total anti-clockwise moment, then we have objects being balanced at equilibrium. Levers and gears. Lever act as force multipliers, and this makes it easier to lift or move loads. Okay, gear transfer rotational forces. The smaller gears turn faster but with less force, whereas the larger gears turn slower but with more force. So gears in contact always rotate in opposite directions. Pressure. Pressure is just force per unit area. That is why we have pressure equals to force divided by area. So increasing the area reduces the pressure and increasing the forces raises the pressure. So in gases, pressure comes from particles colliding with container walls. Pressure in fluids. Pressure increases with depth and density. Okay, so that's why it's the pressures equals to H times P times G. That is the density right there with the gravity with the height. So the upthrust is the upward force on a submerged object due to pressure difference. So an object flows if its weight is equal to the upthrust. The atmosphere gets less dense with height, so air pressure decreases with altitude. Motion, speed, distance, and displacement. Speed equals to distance over time, velocity is speed with direction, and distance already we know is scalar, displacement is also vector. So average speed changes depending on the journey's total distance and the total time. Graphs of motion. The distance time graph, we are made to understand that the gradient is equals to speed, but when it has to do with the velocity time graph, the gradient equals to the acceleration and the area under equals to the distance. So the curve lines the curve lines show changing speed or acceleration, and the terminal velocity occurs when forces balance and acceleration equals to 0. Newton's laws of motion. We have 3 key laws of motion. The first one says that an object stays at rest or moves at constant velocity unless acted on by a resultant force. Whereas the second law states that the force, okay, is equals to mass multiplied by the acceleration. While the third law says for every action, there is an equal and opposite reaction. Stopping distance. In stopping distances, you don't just stop all of a sudden. The first thing is that there's going to be thinking distance plus the braking distance. That is when you have a stopping distance. You want to know where you want to stop, then you know where to actually match the brake. So this taking distance depends on the reaction time. It can be the fatigue, it can be distraction, it can be alcohol. That's what is going to determine your thinking distance. But the braking distance depends on the speed, the road, the condition, the tires and brakes. That's what are going to determine how quick the car is going to stop. So the faster the speed, the longer the stopping distance increases exponentially. Momentum. Momentum equals to the mass multiplied by velocity, and momentum is conserved in collisions and explosions when no external force acts. So in a collision, the total momentum before before collision equals to the total momentum after collision. Changes in momentum and safety features. Force equals to change in momentum over time. So increasing the time taken to stop reduces the forces, and the safety features has to do with the likes of your seat belt, your airbags, your crumple zone, and increasing the safety feature, increasing the stopping time, reduce the rate of change of momentum and further lower the force on passengers, which prevents injury. In conclusion, forces explain how motion changes, how objects deform, and how energy is transferred or conserved. And from Newton's laws to Hooke's law, and from car safety to floating ships, the study of forces help us understand and predict motion in everyday life and advanced engineering. So now we're going to move further by looking at some past paper in regards to the topic we just reviewed.
Let's take a look at few numbers of questions based on what we just discussed. Let's take a look at few numbers of questions based on some of the things we just discussed. All right, so this particular paper highlighted forces and elasticity. The question there says, figure 2 shows a diving board at the side of the swimming pool. You can see your figure 2, the water being highlighted. Okay? You can see the diving board being highlighted. You can see the spring being highlighted. Then it says the original length of the spring is 0.84 meters. Okay, when the child stands on the diving board, the length of the spring decreases by 0.21 meter. Calculate the percentage change. Calculate the percentage change. Okay, so that means that will be 0.21, which is the new one, based on the decrease over the actual, which is 0.84. Okay, multiply by 100%. Multiply by 100%, and that will give us 25%. It's as simple as that. All right, let's take a look at another question. They say write down the equation which links extension to force applied to a spring and the spring constant. On the norm, you will be given a physics equation sheet. So all you need to do is for you to be able to identify the equation so that you can just write it down. However, from what we've discussed earlier on, we know that force equals to the constant, okay, multiplied by the extension. So that will be what? F equals to KE. Okay, and most times, just like I do mentioned, whenever you're asked to give the equation in this manner, do note that the next question will likely be to apply the formula in answering the next question. All right, so if you look at the next question, it says the force applied to the spring by the weight of the shaft is 336 Newton, okay? And the change in the length of the spring is 0.21 meters. And you're asked to calculate the spring constant of the spring. So it's just a formula you're going to use. You know that this is your what? This is your force, okay? And you also know that you have the extension given to you already, which is this. And then the formula is F equals to KE. Since you are looking for the constant, so constant equals to force over extension. And your force is already given as 336 over the extension, which is 0.21. And that will give you what? That will give you 1,600 Newton per meter. All right, let's move on. Let's move on. That's a 6 marker right there. The next question says, a student carried out an investigation to determine the spring constant of a spring. Figure 1 shows the spring before and after a mass was hung from the end of the spring. What is the extension of the spring in figure 1? What is the extension of the spring in figure 1? Okay, they say tick 1 box. Tick 1 box. So how do you determine the extension? How do you determine the extension? From the question, you are already made to understand that the student is carrying out an investigation to determine the spring constant. Okay? And the figure 1 you are seeing there, it shows you the spring before and after it was hung from the end of the spring. Okay, so the first thing you want to look at is before. The before measured 12. This is it. It measures 12. Okay, and after that should be 13.5. So you find the difference, 13.5 minus 12.0, and that will give you 1.5 centimeter. It's as simple as that. So that's the one you expected to take from that particular question. So you just go to a 1.5 centimeter and you take it. Then they say you should give one safety precautions the student should have taken during the investigation. One of it is that the student needs to ensure that they clamp the stand to the desk, or they can also be advised to wear safety goggles or glasses during the investigation. And some other precaution can also be that they need to stand up or away from the apparatus so that they will not influence or affect the recordings as well. So let's go to the next one. They say the student hung a mass of 0.050 kilogram from the spring, and we are given the gravitational field strength to be 9.8 Newton per kilogram. And you have to calculate the weight of the 0.050 kilogram mass. And you have already been given the equation. All you need to do is to put the value. As simple as that. Okay, from the information given, we have been given the mass, and we have also been given the gravitational field strength. So all you need to do is to multiply it. So your weight equals to your mass, which is 0.050, multiplied by the gravitational field strength, which is what? Your 9.8, and that will give you 0.49 Newton as your answer. It's as simple as that. All right. Let's take a look at more questions. They say the weight of the mass applies a force to the spring. The student added more masses and recorded the extension of the spring. Which graph in figure 2 shows the relationship between the force applied to the spring and the extension of the spring? Okay, that is going to be the second one, because as the force is being applied, the extension also increases. Okay, so it's directly proportional, and that is why we have it in that manner. All right, so we now have a question. They say a force of 2.0 Newton was applied to a different spring, and the extension of the spring was 0.080 meters. Calculate the spring constant of the spring, and you are asked to use this equation. Since the force is given as 2 Newton and the extension is given as 0.080, so if you divide this, that will give you 25 Newton per meter. It's as simple as that. All right, let's see if we can take one more question. Let's see if we can take one more question. Okay, let's see if we can take one more question. Okay. They say, question 3, figure 2 shows a balance used to measure the mass of 5 oranges. Ooh. The balance shows in figure 2 contains a spring, okay? Figure 3 shows the spring with no force acting on it and with a force of 6.0 Newton acting on it. Take a look at it. You can see it right there. There's one that no force is acting on it, and there's one that force is acting on it with 6.0 Newton. They say, what is the extension of the spring? What is the extension of the spring when a force of 6.0 Newton acts on it? What is the extension of the spring when the force of 6.0 Newton acts on it? Okay, this is quite very simple as well. This is quite very simple as well. So the first thing you want to do is to convert the value given to you. Before calculating. Okay, if you look at the one of no force, you have 3.5 centimeter. If you convert 3.5 centimeter to meter, that will give you 0.035 meters. Then the next one, when the force is applied, that is 5 centimeter. If you convert this one also to meter, that would be 0.05 meters. So for you to not determine the extension of the spring when a force of 6.0 acts on it, you just probably want to find the difference between the two. And you find the difference by subtracting 0.035 from 0.05. Okay, that will give you your answer regarding the extension, and that will be 0.015 meters. Don't forget to always check the unit before you attempt the question. Okay, then I say calculate the spring constant. Calculate the spring constant of the spring. Okay, you've already been given the force to be 6 Newton. So your spring constant is equal to what? F over E, which is 6 over 0.015, which is the extension. Okay, and that will give you what? 400 Newton per meter. All right, so let's take the last question on this. It says use, okay, they've already given you the equation. They say, what will happen to the spring when the force is removed? No, when the force is removed, just like we mentioned during the course of the material that we reviewed, is that when the force is removed, it will return to its original shape or length. It's going to return to its original shape or length, whereby there was no force applied on it, and that was at 3.5 centimeter. So that's what is going to happen. So I believe you've learned one thing or the other today. Do well to subscribe for more ahead of our next video. Okay, this is Regular Shivers Educational Limited, and we're glad that you are following the platform. So in the next class, we're going to be looking at the next topic for paper 2, Physics AQA GCSE review. Thank you so much for following. See you some other time. Bye-bye.